Heisenberg's Uncertainty Principle by Dave Marsland of Cardiff Theosophical Society. Werner Heisenberg, 1901 to 1976, was a German physicist who made significant contributions to the field of quantum mechanics. He was a pioneer in developing the uncertainty principle, which postulates that it is impossible to determine simultaneously the exact position and momentum of a subatomic particle. Heisenberg first proposed the uncertainty principle in 1927 in a paper titled On the Perceptual Content of Quantum Theoretical Kinematics and Mechanics. Heisenberg's uncertainty principle, also known as the interdeterminacy principle, is a fundamental concept in quantum mechanics that states that certain pairs of physical properties of a particle, such as position and momentum, cannot be measured simultaneously with arbitrary precision, as the act of measuring one of these properties would inevitably disturb the other, making it impossible to determine both with complete accuracy. A mention needs to be made of Planck's constant, which is an essential component in the uncertainty principle. Planck's constant is a fundamental physical constant that plays a vital role in quantum mechanics. This constant is named after the German physicist Max Planck, 1858 to 1947, who first introduced the concept of the quantum in 1900. A quantum is often described as a wave-particle duality, meaning that it behaves both like a particle and a wave. In 1900, Planck proposed that the energy of an electromagnetic wave could only be exchanged in discrete packets or quanta, each with a fixed amount of energy. This idea was revolutionary because it contradicted the prevailing theory of classical physics, which held that energy was continuous and could be divided into any small amount. Planck's quantum theory of energy paved the way for the development of quantum mechanics, which has since become one of the most fundamental and successful theories in physics. Planck's constant is the proportionality constant that relates the energy of a quantum to its frequency, which is the number of oscillations per second. Planck's constant has many important implications for the behaviour of matter and energy at the microscopic level. It explains why electrons in an atom can only exist in certain energy levels and emit or absorb light at specific frequencies. It also explains the wave-particle duality of matter, which means that matter can exhibit both wave-like and particle-like behaviour. The uncertainty principle is often expressed mathematically as an equation for the uncertainty in position and the uncertainty in momentum in relation to Planck's constant. This equation states that the product of the uncertainty in position and the uncertainty in momentum can never be smaller than a certain value, which is determined by Planck's constant. The uncertainty principle has far-reaching implications for our understanding of the nature of reality. It suggests that the classical deterministic laws of physics may not be able to fully explain the behaviour of particles at the quantum level. Rather, the behaviour of particles may be inherently probabilistic and uncertain. The uncertainty principle also introduces the role of the observer into physics, which was a radical change in how physics had been studied, and challenges the assumption that we live in an objective reality that is completely independent of observers. Including the role of the observer in scientific processes and experiments was found in alchemy, but was discounted as alchemy morphed into modern science. The uncertainty principle has practical applications in a wide variety of fields, including microscopy, spectroscopy, and quantum computing. For example, electron microscopy relies on the uncertainty principle to produce images of atomic scale structures. Despite the uncertainty principle's fundamental importance in physics, some scientists have questioned its validity and proposed alternative interpretations of quantum mechanics that do not rely on it. However, most physicists today accept the uncertainty principle as a fundamental aspect of quantum mechanics and a key part of our understanding of the nature of the universe.